Now we start with section 5.1.3, which is guide 5.1.3, and this is we defined air electrostatics. The fundamental thing is charge. So here in magnetostatics, we define the fundamental thing is current, which we call is the charge per unit time. Charge flowing in a unit time, or charge passing to a certain point in a unit time. Then the unit of this will be coulomb per second, and this coulomb per second we defined is ampere. 1 ampere is a big unit of charge. Usually in our ordinary circuits, the current flows at a milliampere level. And the direction of current is also something we need to discuss. We usually take the conventional direction of current from positive to negative. The reality is current flows from negative to positive because it is the electron which flows, not the positive core. So but it doesn't matter that much which direction we do found. And the thing is that if I write this thing is if I write this I is E over T, and I do multiply this thing with a length dimension, then length dimension is L, and here I do L. So this charge per unit length I defined is lambda, the line charge, and L over T is V. So this I define is lambda I, a vector quantity, lambda times V. So Q times V or lambda times V is important. It is not important whether the negative flows or the positive flows, the result will be the same. Just is the one of the assumption by Benjamin Franklin, who did with the glass and fur, and he did almost a notorious or arbitrary example like calling the electron is positive, but that is not the actual thing is it doesn't matter you consider the current flows positive core or due to the electron, the result will be this one. However, is V is involved there, so there may be exception for Lorentz force law and for the Hall effect because the V role is important there. So those are in exceptions, while rest it is the same if we do count it like this. So I can be V lambda times V, or we can write this thing is in terms of even delta T, like V is length times delta T here. So as we have written that magnetic force, the magnetic force is Q and V cos D. So I can write this integral form is V cross B and integration on dq. And then this I can write, this dq I can write is dl, means dq is dl and lambda times dl, because here lambda I defined is charge per unit length. So charge will be I times this L means lambda. Q over L is lambda, so lambda times L will be Q. So lambda dL is dQ. So I can write this thing this is equal to, let me write here, this is equal to V cross G, and here I write lambda dL, and then I do write lambda V here, and lambda V is I, and cross V, considering I is a vector quantity and dl, but here I will not write this dl as a vector because it's a vector itself here. I dl, or if I assign the direction, because current a vector quantity and current gets its direction from the length element, where in which direction the length element is, in the direction the current is. So I can write that F magnetic force is equal to I, and I will keep outside in D down cross V. Now, if I write IDLB and then I write I is a scalar and DL is a vector, then I can come out of the integral and DL cross B. So this is one way we write the magnetic force equation from QV cross B in terms of IDL cross B. And now it's time to move to the solution of example 5.3. So example 5.3 is very interesting, and the statement of the example 5.3 is a rectangular loop of wire supporting a mass M hangs vertically with one end in a uniform magnetic field B, which points into the page in the shaded region of figure 5.10. Forward current I in the loop, would the magnetic force upward exactly balance the gravitational force downward? So let me first go to the geometry of the problem and explain the geometry of the problem that we are having here. Let's say a shaded region. Let me do it here. This is a region, and in this region we have magnetic field. So the magnetic field here, this is the shaded HM, and the magnetic field in this region is into the page. So we have the magnetic field into the page. P is into the page, and this is such that we have a loop of a wire, and to this loop of wire we have attached a mass here, and this is mass M, which is attached to this loop, and current in this loop must go this way, come back this way, in order for the magnetic field to balance the gravitational downward force. Now here is something. If the magnetic field, for example, is into the page, the magnetic field is into the page. Now, if I look at this region, this is out of the shaded region of the magnetic field. Only this is inside the magnetic field, and this will cause magnetic force on this wire. Now this way here and this way downward, they are basically cancelling each other, because in this one the V is going up, while in this one the V or the charges are going down. So the vertical, these segments of this loop, current carrying loop, are cancelling, and the only component which gives support to this hanging mass is this horizontal segment of the loop. And we are going to see this thing further here. So I can say that the magnetic force from this equation, the magnetic force is F equals I times dl and d, and here the width of the loop is basically A. So this length, which is the width of the loop here, this is K. So we have this dl cross B. This dl, when integrate to its total, then it will come out to be A. dl is perpendicular to B. So let me write this thing. F magnetic is equal to I and dl cross D, and dl is running from 0 to A here. Now what about dl cross D? It will become BDL sine of the angle. So the angle means B is equal to the page, and this is dl is in this direction. So we have the angle is 90. So this will come out to be PDL only. Sine of 90 is 1. So DDL, D is constant. It will come out, and DA will come out to be A. So it will, the magnetic force will come out to be IBA. This is the magnetic force that will come out. Now if we say that current is flowing in this one, and that current, the magnetic force balances this weight. So we will write that the magnetic force is balancing the gravitational force, and this implies that IBA is equal to M times G, the gravitational force here. And from here I can write that current is equal to mg over EA. So the value of current will be this much, and the weight just hangs there, suspended in the mid-air. And now what we do, we increase the value of current. We increase I in the loop. Now some source is connected here to this loop, which is responsible for the flow of current. Here let's say the source may be a battery or a generator, and when current is increased here, then what will happen? The imbalance will be affected, and the magnetic force will become more than the weight, the hanging weight. And as a result, what will happen? That this mass will be lifted a bit up. And then a question arises that magnetic force does not work. And we see that this is being lifted up. Then who is doing the work? If it is not magnetic force, then what force is responsible for the work? Apparently, it seems the magnetic force is doing this work. So we are behind the agent who is lifting the stick up. Now here, the what will be the work done here when force is this much? The work done by the magnetic field will be, this is force, so force time distance. Let's say it is up by distance h. So IDAH is the work which is done by the magnetic force here uh, in lifting this loop up. So IBAH, and it seems that the magnetic force is doing this work. And from our earlier discussion, we know that magnetic force does not work. So we are behind the agency who is doing the work. We are behind the force who is doing this work. Now let's say, if I look this thing carefully, then, well, for example, this will be lifted up. What about the motion of the charged particle? Like the particle at instant is here and it is moving in this direction, but when it will be lifted up, then the direction of the particle motion will be something like this, and here and here. So it is something like this, and here you see that this is the actual path of the particle. So an upward component has been added to this one, and that upward component is u component of, or the velocity which is responsible is u here, while this is the actual velocity with which it is going in that direction. When there was no force, then when there was no increase in the current, no lifting up, the velocity, the horizontal velocity was w. But this additional component, due to the increase of current, this additional component came in and the net velocity is now in this direction. So let me make this figure carefully. Like this is w, the horizontal velocity in this direction, and then another velocity heats up with this one, and this velocity is basically u here, and this makes the resultant is this, which is v here. This is v. Now what about their respective work done? The respective work done will be, like when this is v, then the magnetic force will be perpendicular to this one, and it will be something like this, means just make it perpendicular to it, and like this. So this is the F magnetic. This is the magnetic force, and the for the Q, for the other, I'm writing it in another form. Like this will be when okay, this is charge Q, and to this W velocity, the force will be perpendicular to this one, and this force is equal to QWB, because QV cross B is they are perpendicular to each other, so it will become QWB, and it is in this direction. The net motion is in this direction, so now it is U, so perpendicular to U will be this one. So if I'm writing it here, means I am writing it here. So this will be QUV. This will be the force for that U component here. Now if we look carefully to this thing, then this is the net magnetic force here. This one, this component, the QWD force is responsible for lifting it up. It is the vertical force here. And this QUB, which was the result of this U, like moving it up. So the force is basically opposing the motion in the direction.